Now, precipitation reaction. So precipitation in chemistry does not mean raining. Precipitation is when you make a solid from adding two aqueous solutions together. So a solid is produced from mixing two things that are completely dissolved or completely dissociated. For example, when you put silver nitrate and potassium chromate together, you get a solid. I'll show you what it looks like. Okay, so this is a video of adding potassium chlorate and silver nitrate. Oh, chlorate, not chromate. Okay, the typo. So notice this is a clear yellow solution. It's completely dissolved. It's not cloudy or anything. And if you add some of that silver nitrate, you get this solid made in there. This is a precipitate. Whenever you put a compound that's completely dissolved, so that yellow was completely dissolved, it was clear, with the silver nitrate, which was also clear, and you make a new solid. That is a precipitate. This was potassium chromate and silver nitrate. Okay, so if I go back here. Okay, so when I add these together, I have silver nitrate, which was aqueous, with potassium chromate, which was aqueous. I make what is that new solid? Okay, so how did I figure out this was a solid? Well, first of all, based on our types of reactions in the last unit, we know that when we add a compound to another compound, this is going to be a double replacement reaction. Means that my ions are going to switch places. So the silver is going to switch places with the potassium. So before I even figure out what the solid is, I would be like, okay, well, the silver now is going to go with the chromates and the potassium now is going to go with the nitrate. So I switch them. Now I've got potassium nitrate and silver chromate. Notice though, silver did not have a 2 here, and it does have a 2 over here. And that's because anytime you put those new compounds together, you have to check your charges. Okay, so chromate had a -2 charge, silver is always a +1, so it's Ag2CrO4. So these are my two compounds, and then I'm telling you this is my solid, and this one was aqueous. I'm going to tell you how I figured that out. So if it looks cloudy, it made a solid, it made a precipitate. Okay, so the precipitate is the solid, which is insoluble. And then I went ahead and balanced this. So I'm going to go a little bit more into how to write these precipitation reactions. So there are actually 3 different types of equations I could ask you to write. The one that we've been writing, the things that we've been balancing look like this, are called molecular equations. There's also complete ionic equations and net ionic equations. So those are the 3 types of equations that I can ask you to write. Okay, so I'm going to start with molecular because this is what we've been doing. This is a regular balanced equation. It shows all of your compounds. It doesn't have any charges written. Okay, so like when I'm writing this, yeah, I check my charges to figure out, okay, well, Na is +1, Cl is -1, so it's NaCl. Ag is +1, NO3 is -1, so it's AgNO3. I check my charges, but you don't write them, okay, right? Everything balances out. So sodium chloride and silver nitrate make AgCl, which is a solid, and sodium nitrate, which is aqueous. Now, how did I figure that out? All right, so I went to the next page really quick if you want to flip the page. These are our solubility rules. This is actually going to tell us which thing is going to be soluble and which thing is going to be insoluble, or which thing is going to be my precipitate. Okay, so these are the rules, and this is how you read them. So rule number 1, sorry about that, is this applies to anything that has a lithium ion, sodium ion, potassium ion, or an ammonium ion. If those are in your compound, they group 1 and ammonium compounds, so these are group 1 metals, this is ammonium, are soluble with no exceptions. So anytime you have something with a lithium, a sodium, a potassium, or an ammonium, it's soluble. So if I look back at the equation I was using here, okay, Na is on that list for group 1. So this is always soluble no matter what, because it has an Na+ ion in it. Now let's look at this one. This did not fall under group 1. So I'm going back down here. Under group 2, anything that has an acetate ion, C2H3O2-, or an NO3 and nitrate ion, those are soluble with no exceptions. I'm going back up here. AgNO3, this has the nitrate in it. This is soluble, no exceptions. So anything with a sodium, anything with a nitrate, they are going to be AQ for aqueous. That's because they are soluble. Okay, so now over here, so what I did next is I switched my cations. So now the silver is with the chloride and the sodium is with the nitrate. So my products are AgCl and NaNO3. I did recheck my charges, but everything over here was +1 and -1. So that's balanced. Now, how did I determine this was solid and this was aqueous? Well, first of all, according to my first and second rule, anything with sodium and anything with nitrate is soluble, so it's aqueous. So how did I know this one was solid? Well, it didn't work under rule number 1 or number 2. However, if you look at rule number 3, got a chloride ion right there. I'm talking about AgCl, right? I'm trying to figure out if that's going to be soluble. Well, it has chloride in it. Most chlorides, bromides, and iodides are soluble, except if they are with silver plus, mercury, or lead 2. And in my case, I have Ag plus with Cl minus. So this, if it's gray, that means it's going to be a solid. That's going to be my precipitate. It is insoluble. So that's how I figured out that this was my solid. Okay, so this is my balanced molecular equation. Now I should have checked my charges over here again, but again, they're all +1, -1, so everything is balanced out. This is normal. Now the next type of equation is called the complete ionic equation. And in reading that, you should be like, okay, I need all of the ions. So what you do is from your molecular equation, now you're going to break aqueous substances, anything that's aqueous, into their ions. So you do have to actually show the ions. They have to have charges. So if I'm looking here, I have, well, this is aqueous, so I need to break it into its ions. This is aqueous, I need to break it into its ions. This is solid, so you do not break it up. And this is aqueous, so you break it into its ions. So I have Na plus and Cl minus. I have Ag plus and NO3 minus. So this is what I'm combining. And then my products are this solid, do not break up the solid. And I have Na pluses and NO3 minuses in there. These should show your charges when you break them into their ions. Now I wrote aqueous after all of these. If you don't do that, that's okay. As long as I know which one is solid, if you drop these little aqueuses, that's okay. Okay. So one thing to note when you are breaking those aqueous ions, or breaking those aqueous things into ions, if it has a subscript for that ion, so if this had been like Cl2, that 2 would become a coefficient. It should go in front. Okay. This is except for polyatomic ions, of course. So if I look at this, say I had this aqueous, this potassium chromate, this is the one we were talking about in the example before. When this breaks up, I actually have 2 potassiums. So this little 2 becomes a coefficient. So I actually have 2 K pluses in my solution. It should not be K with a little 2 here. Okay. Now this is a polyatomic ion, CrO4 2 minus. Polyatomic ions don't break up, they stay as a thing. So CrO4 2 minus is on our polyatomic ion sheet, that's chromate. So the 4 does stay because it is part of the polyatomic ion. So if the subscript is part of a polyatomic ion, it stays when you break it up. But if the subscript is not part of a polyatomic ion, it needs to go in front as a coefficient. Okay, so if this had been in my equation, it should look like this when I break it up for my complete ionic equation. And finally, the net ionic equation. The net ionic equation really comes in handy because it tells me really what's going on in the chemical reaction. What did I do? So it shows the new solid that you made. And that's it. It just shows me the precipitate. Okay. So what you're going to do is you are going to, from your complete ionic equation, you are going to drop the spectator ions. Okay, so you might be like, what's a spectator ion? Well, a spectator ion, as the word spectator indicates, is something that watches. Spectators don't participate. The spectator ions are the things that are just floating around there. They don't participate in the chemical reaction. So if you look up here at my complete ionic equation, the spectators are anything that is exactly the same, meaning it's the same state of matter and the same charge on the left and the right. So for example, sodium plus is the same on the left and on the right. Cl minus is not. Cl minus is now an AgCl over here, but NO3 minus is still NO3 minus over here. So my spectator ions were Na plus and NO3 minus. They didn't actually do anything. They stayed exactly the same. So you drop those to make your net ionic equation. So again, those spectator ions are the ones that are just floating around. They don't interact. They don't do anything. They're exactly the same on both sides and they would cancel out. So this Na plus cancels with this Na plus. They have to be exactly the same. So then I am left with Cl minus plus Ag plus makes AgCl solid. So what this equation is showing me is exactly the chemistry that I did. AgCl is my solid. Na plus and NO3 minus didn't actually participate in the chemistry, so this is what happened. Okay, now if I were to draw like in a beaker what my final products were once I put everything together, this is what's really going on. I made this solid, and then of course the solid is going to settle at the bottom. So we write AgCl, and I got my little S there. This is just showing that it's settled on the bottom. And then those spectator ions should still be floating around in the solution. They don't make a solid, they don't do anything. They are my spectators, they're just floating. So whatever made your solid, that's what should be part of your net ionic equation. Okay, so I'm going to look here at these solubility rules again really quick. I kind of showed you how to read them. Once you get past number 4, anything that has a carbonate, so CO3 2- in it, is insoluble. So anything with a carbonate is insoluble unless it had something from rule 1. So like if it was a lithium carbonate, that would be soluble. But anything else besides these 4 with carbonate would be insoluble. Okay, that's kind of how you read it. And then if it's not on the chart, it's probably insoluble. Just kind of keep that in mind. So what I want you to do is look at example 2 and example 3 to show how to do dissociation. And then we'll talk a little bit more about writing the equation. So go ahead and give these a try and then check your answers. So using these solubility rules, I'm going to label each of these as either aqueous or as a solid. That's what the S stands for. It is insoluble. S does not mean soluble, so keep that in mind. Okay, so I've got AgNO3 here, or silver nitrate. I would be like, okay, well, nitrate is part of rule number 2, always soluble, so it gets an AQ. PbBr2, well, Br is right here, which is soluble unless it's with one of these things, and in this case it is. So that would be a solid. It is one of those exceptions. Okay, BaCO3 is a solid because of rule 5, insoluble. This one is aqueous because of rule 1, K+ is always soluble. And FeS is a solid because of this here, solid S sulfur, are insoluble unless they're with rule 1. Okay. Then I wanted you to show what happens and write their dissociation equations down here. So dissociation equation is what ions they break into. So for example, NaCl breaks into Na+, and Cl-. So this is good practice to get ready to write your complete ionic equations. K2SO4 should be, this 2 should become a coefficient, right? Be 2 K+, and 1 SO4 2-. That's a polyatomic ion. So have your polyatomic ion sheet next to you as well. Okay, CaBr2 and then AlNO3 3. So this 3 out here means I have 3 of the things in parentheses, which is a polyatomic ion. So the nitrate stays together, NO3-, but this 3 goes in front because I have 3 of them. Then what does that look like in a beaker? You need to show the correct ions. They do need to have charges and the correct numbers. So if you're looking at C, for example, I have 2 K+ and an SO4 2-. So this is good practice to show me what those compounds, when you dissolve them, what they look like floating in solution. And kind of as a side note here, you are not going to have to memorize these solubility rules. These will be given to you on the exam.